Hi everyone, in this video we are explaining example 6 from lesson 3. In this example we have a three-phase motor with 4 poles, a frequency of 50 Hz, which is rotating at that velocity, 1450 revolutions per minute, and they ask about the sliding. As you know, the sliding depends on the synchronous velocity, and the sliding is going to be the synchronous speed minus the speed we have in this situation and divided by the synchronous speed. That means that we need to obtain first the synchronous speed. The synchronous speed is going to be 60 times the frequency divided by the number of pairs of poles that we have, okay? So here we have 60, the frequency was 50 Hz. And we have 4 poles. That means that the number of pairs of poles that we have is 2. So that gives a result of 1500 revolutions per minute. So then the sliding will be the synchronous speed minus that speed there and divided by the synchronous speed, which gives this result approximately, which expressed in percentage gives 3.33%. Now we are at example number 7. So there you have a motor with 4 poles and a frequency of 50 Hz. And in this example, they ask the frequency of the induced current, which is F2, in different situations. So then you need to know that the frequency of the induced current is going to be the sliding multiplied by the frequency of the motor. As the frequency of the motor is 50 Hz, what you need to do is to calculate the sliding in different circumstances. In the first question, question A, they say that the rotor is blocked. So if the rotor is blocked, its speed is 0 revolutions per minute. That means that the sliding, which is the synchronous speed minus that speed and divided by the synchronous speed, will be the synchronous speed here, when we have a motor with 4 poles and 50 Hz of frequency, will be the same as in example 6. It would be 1500 revolutions per minute minus 0, okay? And divided by the synchronous velocity. So as you can imagine, here the result that you're going to have is sliding equal to 1. That means that the frequency of the induced current is going to be the sliding 1 multiplied by the frequency of the motor. So in this case, 50 Hz. In question B, they say that the angular speed is 400 revolutions per minute in the same sense as the rotating field. So then, the sliding will be the synchronous velocity minus that speed and divided by the synchronous velocity, which gives a result of 0.733. So that gives a frequency of the induced current equal to 36.67 Hz. In question C, they say that the speed is 2000 revolutions per minute, and we have the same sense as the rotating field. So when we try to calculate the sliding, what you have, so as we can never have a negative sliding, we need to do this in the numerator in absolute value. And we are going to get this result here. You need to know that as this value is higher than the synchronous speed, then the motor is working as a generator. So with that sliding, there you will have a frequency in the induced current equal to 16.67 Hz. So now in question B, we have that the angular speed is 1000 revolutions per minute, but now in opposite sense as the rotating field. So what is the meaning of that? Okay, the meaning of that is that you need to consider this as negative, okay? You need to consider this as negative because its sense here is opposite to the rotating field. That means that when you try to calculate the sliding, so in this situation you are going to get a sliding higher than 1. That means that the frequency in the induced current is going to be higher than 50 Hz. In particular, it is going to be 83.33 Hz. We are in example 8 of lesson 3. In this example, we have a three-phase motor whose synchronous speed is 1,500 revolutions per minute, and the motor is working at a frequency of 50 Hz. So, in the first question, they ask the active power coupled from the stator to the rotor. The active power is going to be the same as the absorbed active power minus the iron losses and the thermal copper losses. So that is 100 kilowatts. And here the sum of these two losses is 10 kilowatts. So the result is 90 kilowatts. That is the active power coupled from the stator to the rotor. In question B, they ask the Euler copper losses in the rotor. So, as you know, the copper losses in the rotor will be the sliding multiplied by the active power coupled from the stator to the rotor. So we need to calculate the sliding, for which we need to do the synchronous speed minus the effective speed that we are having divided by the synchronous speed. So that is this minus this divided by 1,500, which gives a result of 0.1. So the sliding is 0.1, and the active power coupled from the stator to the rotor is 90 kilowatts. So that gives 9 kilowatts. In question C, they ask the mechanical power developed in this situation. As you know, the mechanical power is going to be the active power coupled from the stator to the rotor minus the copper losses in the rotor. So that is 90 kilowatts minus 9 kilowatts, which gives 81 kilowatts. Finally, in question D, they ask the efficiency of the motor. The efficiency of the motor is going to be the ratio of the electric power divided by the absorbed active power. As you know, the electric power is the mechanical power minus the power of mechanical losses divided by the absorbed active power. If we suppose that the mechanical losses are negligible, then we will have the mechanical power divided by the absorbed active power, which will give a result of 81 kilowatts divided by 100 kilowatts, which is 0.81 or 81%. And with that, we have solved example 8.